Let's dig into steady-state stability in more detail now, based on the next few slides. It brings us back to that power angle, delta.
Yes, steady state stability. It's fundamentally about that power angle, delta, and its behavior during small, gradual changes. The material reminds us changes in delta happen because of relative acceleration due to torque imbalances.
Right.
Steady state stability is the system's ability to maintain synchronism, to find a new stable angle after these small, slow disturbances. Think normal load changes during the day.
And the definition given is angular stability, restoring the angle within limits after acceleration. It says operators have control in a stable system but lose it when stressed.
That's the key. When the system has good steady state stability, the green zone, as the presentation called it, there's enough synchronizing torque. Small changes happen, parameters shift gradually, but the system smoothly finds a new equilibrium.
Like the example given, 400 kV, 1 ohm impedance line,
Yeah.
0 degrees angle, 0 milliW, 30 degrees angle, 80 milliW transfer.
Exactly. And that example calculates the maximum power, Pmax, for that setup as 160 milliW, which occurs at 90 degrees.
Right.
So operating at 80 milliW with a 30-degree angle is comfortably below that 90-degree peak.
Right.
There's a clear stability margin showing the gap between the operating point 30 degrees and the theoretical limit 90 degrees.
So being in that margin is stable operation. And steady-state instability, the red zone, happens when you get pushed too close to that 90-degree limit or beyond it.
Correct. If load increases and you need to transfer more power, the angle increases.
Yeah.
As it approaches 90 degrees, that restoring synchronizing torque gets weaker. If you push it too far, close to or past 90, the system can't find a stable equilibrium.
It loses the spring force.
Essentially, yes. Past the peak, trying to push more power makes the angle run away, leading to loss of synchronism. The graphs in the material show this clearly. The stable case settles, the unstable case shows the angle just increasing indefinitely.
The presentation then brings up power transfer limits and these N1, N11, N2 criteria. How do those connect to steady-state stability?
These are crucial planning standards. N1 means the grid must remain stable, including steady state, stable, even if any single major component fails unexpectedly, a big line trips, a large generator goes offline.
Okay, handle one failure.
N11 means handle one failure and then another one happens before you can adjust. N2 means handle two simultaneous failures. Planners use these criteria in offline studies to figure out the maximum power you can safely schedule across transmission paths, ensuring you still have enough steady-state stability margin even after one of these events occurs.
So meeting N1 means making sure that even with a line out, the remaining paths aren't pushed to that unstable red zone for the power they need to carry.
Exactly. You need enough margin built in. And the material lists several ways to improve or maintain steady-state stability.
Like voltage improvement. How does that help?
Well, remember the power transfer equation. Pmax depends on V's and VR, the voltages. Keeping voltage levels strong helps maximize that Pmax.
Higher Pmax means you can transfer the same power at a lower, safer angle.
Precisely. So maintaining voltage requires managing reactive power, MVAR. The presentation mentions using generator excitation controls, adding capacitor banks to supply MVAR, reactor banks to absorb it, and switching them as needed.
Okay, so voltage support via reactive power is key. What else?
Reducing path impedance, X in the equation. Lower impedance also means higher Pmax, again allowing lower operating angles. You can do this by building more parallel lines or using series capacitors to effectively cancel some line reactance.
It makes sense.
Also, generation redispatch. Shifting generation closer to loads reduces flows on long, high-impedance paths, lowering angles. And using HVDC links can bypass AC angle limitations altogether for bulk power transfer.
All right, let's shift gears to transient stability. This is for the major turbulence, the big hits like faults.
Yes, transient stability.
Mm-hmm.
This is about whether the system can stay synchronized after a large, sudden disturbance. A short circuit, a fault, is the classic example.
How does a fault cause this kind of instability?
Well, a severe fault, as the material explains, dramatically changes the grid's impedance. It can essentially block or severely limit the generator's ability to send its power out onto the grid.
But the turbine is still pumping in mechanical power.
Often, yes, at least initially. So you get this huge sudden imbalance. Lots of mechanical power in, very little electrical power out. This creates a massive acceleration torque on the generator rotor.
Causing the angle to swing wildly and rapidly.
Exactly. The rotor accelerates hard and the angle shoots upwards very quickly. If that swing is too large, too fast, meaning the fault isn't cleared quickly enough or the system is weak, the angle can swing past the point of no return and the generator loses synchronism.
And the time frame here is incredibly short, the presentation notes. High impact and small duration of time, 10, 200 meters, fractions of a second.
It's why protection systems have to be lightning fast. Transient stability is decided in cycles, not seconds or minutes. If the protective relays don't detect the fault and open the breakers almost instantly,
Too late.
it can be. The system needs to clear the fault and restore a path for power flow before that angle swings too far.
The example given makes sense. Generator accelerates during the fault. Fault clears, path restored, it starts decelerating. But if the acceleration push was too big compared to the deceleration pull, the system can provide afterwards.
It overshoots and loses sync. This is often analyzed with the equal area criterion comparing acceleration energy gained to deceleration energy capability.
And the consequences are severe. Power plant blackouts if units trip out of step, or even cascading system-wide blackouts. The 2003 U.S. blackout is mentioned as an example.
Yes, major events highlight how critical this is. Preventing it involves limiting that initial acceleration and ensuring rapid recovery. The materialists' measures split into long-term planning and operational planning.
Okay, long-term planning.
This is about building a robust system. Things like installing high-speed protection relays and breakers to clear faults faster. Reducing transmission reactance, more lines, series capacitors makes the grid stiffer. Improving power transfer during swings. Using generators with fast-acting excitation systems, AVRs, helps maintain voltage during disturbances. Dynamic reactive support from STATCOMs, SDCs, also helps voltage. And specific turbine controls like fast valving can quickly cut mechanical input power for a moment.
And operational planning. What can be done in real time or near real time?
This involves things like system protection systems, SPS, or remedial action systems, RAS. These are automated schemes. If they detect a specific critical event like a major line trip, they automatically take pre-planned actions, like tripping specific generators or loads elsewhere, to quickly rebalance the system and prevent instability faster than human operators could react.
Wow, automated emergency actions.
Yes, and also ensuring transmission line auto-reclosure works correctly. Many faults are temporary, like lightning flashes. Auto-reclosure quickly tries to close the breaker back in, restoring the line hopefully before instability sets in.
The final slide on this section lists specific examples again. Fast protection, FCTS devices, digital AVRs, turbine bypass, SPS RAS, auto-reclosure on high-voltage lines.
These are the concrete tools and strategies deployed to bolster the grid against those sudden large shocks.
Okay, next up is dynamic or oscillatory stability. The presentation starts by comparing the power system to a spring mass system, saying it has an inherent oscillatory nature.
That's a good analogy. Because you have these rotating masses, generators, connected by electrical springs, transmission lines, the system naturally tends to oscillate or swing when disturbed.
Like pushing a swing.
Kind of, yeah. Dynamic stability is all about making sure these natural oscillations, which happen after even small disturbances, are quickly damped out. They need to fade away, not persist or grow. And this, the material says, requires good damping torque.
Where does the damping come from? It mentions natural damping, like I2R losses, friction.
Yes, the system has some inherent passive damping. Electrical resistance dissipates energy. There's mechanical friction. Some loads help damp things. But often this natural damping just isn't enough, especially in big, complex grids.
So you need more.
So we rely on force damping, which is actively added by tuning control systems correctly.
And the oscillations we're talking about are these low-frequency oscillations, LFOs,
Yeah.
0.2 to 3 hertz, much slower than the 50-60 hertz power frequency.
Exactly. These LFOs represent energy sloshing back and forth between different groups of generators or different regions of the grid. It's the generator's rotors swinging relative to each other. The material notes usually see one group swinging against another.
And it also mentions unit oscillation due to controller issue. So sometimes it's not the whole system, but maybe one generator's control is causing problems.
That can definitely happen. Poorly tuned controllers on a generator, its exciter, its governor, maybe poorly set power system stabilizer, PSS.
PSS.
Yeah, power system stabilizer. It's a device specifically designed to add damping via the excitation system. The slides don't detail it, but it's a key tool.
Yeah.
Anyway, if these controllers are badly tuned, they can actually reduce damping or even create negative damping, making oscillations worse.
Okay, so what happens if these oscillations aren't damped properly? What's the impact?
It can be pretty bad. As listed, you get wide swings in voltage, power angles, power flows across lines. These swings can confuse protection relays, causing unnecessary trips of lines or generators.
Which could cascade.
Exactly. It also limits how much power you can safely transfer, because high transfers often reduce damping margins. You might get local oscillations within a plant, or wider inter-area oscillations between regions.
And it mentions long-term effects like wear and tear on generator shafts from the constant mechanical stress, hidden failures, and ultimately wide-scale blackout. It even links specific historical blackouts in 2003 to LFOs.
Yeah, uncontrolled growing oscillations are a known pathway to major grid collapses. They destabilize everything.
So the fix is enhancing damping torque. How's that done?
Primarily, as the material says, through careful tuning of controlling devices. Getting those exciters, governors, and PSS settings just right is critical.
Okay.
Other measures include operating within established transfer limits that are known to be dynamically stable, quickly identifying and isolating anything causing or amplifying oscillations, sometimes reducing power flow on troublesome tie lines, maintaining a strong transmission network generally helps, and keeping power angles lower, as damping often degrades at high angles.
So it's a mix of smart controls and careful operation. The graph showing how tuning improves damping really highlights the control aspect.
Absolutely. Active control is essential for managing these inherent oscillations.
In the third part, we will learn on frequency and voltage stability and stability assessment tools for planners and grid operators.